Hello, everyone. This is Vibhav Agarwal from Samsung Research, Bangalore, and I'll be presenting our work on a lightweight on-device intent detection model using Deep Siamese Network. With the billions of text data being generated every day, natural language processing is becoming more and more important to make sense of the unstructured data and use it in many applications through syntactic or semantic analysis. So one of the forms of NLP is intent detection. So these are the applications. So basically, what is intent detection, or also known as intent classification? So it means identifying intention behind user input, and it is a crucial task in any natural language understanding systems. Example, chatbots or intelligent virtual assistants. So we can see from these examples that understanding the primary intent of the context communication is critical for offering natural language responses or providing intelligent suggestions. For example, in this, we can see, right, when is the next meeting? The intent of the user is probably the calendar. From where we have to extract the relevant event. And whereas the second example, we can see the intent could be location, where the user is asking about the second person's location. So we propose a lightweight model, LIDSNet, to accurately predict message intent with very much less latency and memory footprint than SOTA on edge devices. We curate our own custom dataset for conversational messages with these intents, notes, calendar, location, contact reminder, and greetings. And we utilize Siamese network with triplet loss for generating better sentence representations. The experiments in our work are carried out on custom dataset, which we curate ourselves, along with public datasets, SNIPS and ATIS. The custom dataset we prepare by merging intents from two datasets, which is Clinic 150 and HW 64 datasets, and we merge those intents from these two datasets into 6 categories, so which are mentioned here. And using this approach, we extract around 4.1K samples mapping to these 6 intents. Further, we prepare an unsync test set of 300 samples belonging to these 6 intents only, which are generated by crowdsourcing conversational text. And here we can see the distribution of the data in our training custom data set. So talking about data representation techniques, we use the combination of word level and character level input representations to generate final representations. This is because word representation is suitable for relation classification, but normally it does not perform well on short informal text, whereas character representation effectively handles misspelled and out of vocabulary words. So our model, in our model LIDSNet, we use 2 CNN blocks with different kernel sizes to capture multiple character level n-gram features, which are then concatenated with pre-trained word embeddings. So let's move to our proposed model architecture, which we can see here in this figure. So in this, our proposed architecture, we use Siamese network. So Siamese network with triplet loss consists of identical subnetworks with shared weights. Our proposed model consists of a sentence encoder that is trained in 2 phases, basically. So in training phase 1, we apply transfer learning by using a subset of pre-trained word embeddings that capture semantics. These embeddings are then concatenated with character level features of the corresponding words. The resultant word level features are then fed to a BERT layer to obtain the sentence level representations. With this training phase, our aim is to tune the weights of the shared neural network in a way that it is able to segregate and create a distinction between the sentencing embeddings of the same intent and different intent training sequences. So that is why that A and P and N represent anchor positive and negative, where anchor and positive belongs to the same class and N, which is negative, belongs to a different class. And that's how this is how our triplet loss is computed. In training phase 2, which is basically this phase, we pass those representations through a feed-forward neural network, which acts as a classifier to compute the probability distribution over the defined intents. So now moving to our experiments. So first is the ablation study, where we investigate the effect of different architectural choices what we made during preparing our architecture, and the results of which are presented in the table shown. Uh, so basically, we kind of generate three different. We can see six different variants, in which first is the 1p random, which is the base classifier. Then 1p glove, in which we only use the classification phase along with the pre-trained glove embeddings. 2p char, in which only the character embeddings are used. Random, in which no pre-trained embeddings are being used. 2p fastx with the fastest embeddings, and 2p glove, which is the final model, which we call it as LIDSNet, is training in two phase along with glove pre-trained embeddings. So let's see the results. From the results, we can observe that LIDSNet achieves absolute accuracy improvement of 1.29% and 0.56% on SNIPS and ATIS respectively, when compared with 1p glove classifier. Also, the impact of glove embeddings can be seen from the fact that LIDSNet achieves 1.14% and 0.45% improvement over 2p random classifier on SNIPS and ATIS respectively. So we can see the effect of pre-trained embeddings helping in improving the classification accuracy. And the model sizes of LIDSNet when trained on these two public datasets, SNIPS and ATIS, are only 0.63 MB and 0.12 MB. So in this performance analysis, the left side graph illustrates the effect of varying hyperparameters on model accuracy. So a margin of 0.02 and 24 hidden units in LSTM give the best results as per the experiments, as illustrated in these figures. Towards right, we have confusion matrices summarizing the classification performance of LIDSNet on SNPs and custom test data. So we compare our best model, LIDSNet, with other SOTA methods on both the public datasets, SNPs and ATIS. Table on the left shows that LIDSNet achieves SOTA competitive accuracy with the lowest memory footprint. For SNPs dataset, we achieve the second highest accuracy of 98% with the lowest model size of 0.63 MB. This can enable effective deployment of LIDSNet on edge devices such as mobile phones, on watches. Also, we benchmark our model's latency against fine-tuned BERTs. Model inferencing experiments, whatever are shown here, are conducted on the Samsung Galaxy S20 device. And we can see that our model has a maximum inference time of only 18 milliseconds, which is 87 times faster than BERT-based and around roughly 30 times faster than MobileBERT. So to conclude, we propose a lightweight, fast, and accurate LIDSNet model for intent classification. Our experimental analysis on SNPs and SNPs, ATIS, and as well as our self-curated custom dataset proves that LIDSNet achieves SOTA competitive accuracy with the lowest memory footprint, which is very crucial and critical for a commercial conversational AI solution. And in future, we plan to develop a joint model for intent detection and slot filling. And at the same time, we wish to extend it for other languages apart from English. Thank you.